Okay, today we want to look at the concept of titration problems and look at the types of problems that we can solve with acids and bases that will lead into the lab that we are going to do at the end of the week and lead us into the types of calculations that work through a lot of the stoichiometry problems that come out of acids and bases. When we're doing a titration problem, we're mixing an acid and a base and using the known concentration of one to find the unknown concentration of the other. To do this, we usually use an indicator solution. So I'm going to start with indicator solutions, and then we're going to work our way into the titration problems. An indicator is a large molecule that can act as a weak acid or base. So you have, for example, here, I've just taken the molecule and called it IND. It would be some large, usually organic molecule. When it has the hydrogen, it acts as an acid. When it doesn't have the hydrogen, it acts as the conjugate base. The acid and the conjugate base are different colors, so whether there's more of the acid or more of the conjugate base will determine the color of the solution. So we undergo a color change depending on the H3O plus concentration. If there's more H3O plus concentration, the reaction will go in reverse, producing more of the H indicator with the hydrogen. If there's less of the H3O plus, it'll go forward, producing more of the indicator without the hydrogen, and those are two different colors. There's a chart in your textbook of all the different indicators and the different colors and when those color changes occur based on the pH. Now when we're looking at a titration problem, we're taking the known concentration of one reactant and using it to find the unknown concentration of another reactant. For example, we could know the concentration of an acid, know the volume of the acid, know the volume of the base, and use that to solve for the concentration of the base, or vice versa. When we get an equal concentration of acids and bases, we would call that the equivalence point, or it's the point at which the concentration of H3O plus or H plus is equal to the concentration of OH minus. That's going to be very helpful for us, because when the concentration equals each other, the number of moles equal each other, and that's how we're going to go about solving these problems. Finding the moles of one of them, setting up the stoichiometry, so the moles of acid and base are equal, and then solving for the other one. Let's look at some examples of this. Now, I would highly recommend as you're watching these videos that you take the time to pause the video, try the problem yourself, see if you're getting the right answer, and then when you go back to play it. So this first one, 50 milliliters of a 5.0 molar HCl solution is placed in a beaker. How many milliliters of 5 molar NaOH will be needed to titrate the HCl? So the reaction we're looking at here, HCl plus NaOH reacts to form NaCl plus H2O. NaOH is the base, HCl is the acid, double replacement reaction from acids and bases. So we're going to start with the HCl. We have 0.0500 liters times 5.0 molarity. Remember, liters times molarity will give us moles. When we multiply that together, we get 0.25 moles HCl. Now we can go from moles of HCl to moles of NaOH. This is the stoichiometry step. So there's 1 mole NaOH for every 1 mole HCl, which means we'll get 0.25 moles of NaOH in this reaction. Now we need to find the number of milliliters from the molarity. We know molarity, 5.0 molarity equals moles, 0.25 divided by the liters. Cross multiply, 5.0 molarity times X equals 0.25. Divide both sides by 5. go get our answer in this case. It comes out to 0.0500 liters, or 50 milliliters. Now we end up actually in this case with the exact same number as the milliliters of HCl. That is due to the fact that in this case the concentrations are the same. They're both 5 molarity, and it's a 1-to-1 ratio. In this problem, we start a little bit differently. We don't have a 1-to-1 ratio, and we're starting with grams. Once again, write the balanced equation first. In this case, double replacement again, the products will be water and the ionic salt, which in this case will be magnesium chloride. In this case, we get a 2-to-1 ratio of acid to base. We're going to start with grams of the base, magnesium hydroxide in this case. Our first step is to convert that to moles. So we're going to use the molar mass, 1 mole magnesium hydroxide. The molar mass of magnesium hydroxide can be found by adding magnesium, 24.31, plus 2 oxygens and 2 hydrogens, so 58.33 grams. We come out with 0.02057 moles of magnesium hydroxide. I'm not going to round to significant figures yet until the problem is completed. Then we want to go for moles of magnesium hydroxide, 0.02057 moles. We want moles of magnesium hydroxide on the bottom. We want moles of HCl on the top. So we multiply by 2. In this case, we get 0.0411 moles of HCl. We're trying to find concentration, so it's moles divided by liters. 0.0411 moles divided by 0.4500 liters. That comes out to a concentration. Now I'll use my significant figures of 2 significant figures, 0.091 molarity. So in this case, we converted grams to moles, then used the mole-to-mole conversion, then went back to concentration. Next question, 24.3 milliliters of 3.5 molar HCl is added to 40 milliliters of unknown concentration NaOH. The equivalence point is reached, so it's been titrated. There's an equal concentration of acid to base. What is the molarity of NaOH? So start with the balanced equation. HCl plus NaOH forms NaCl plus H2O. 0.0243 liters times 3.50 molarity to get us the moles of HCl, which in this case comes out to 0.08505. We're going to convert to moles of NaOH. Say 1-to-1 ratio. So we're going to end up once again at 0.08505 moles NaOH. We're looking for the concentration, so we're going to divide that number by the liters. 0.0400 liters of NaOH. So divide 0.08505 by 0.04, and we get 3 significant figures, 2.13 molarity. The final problem, 83.1 milliliters of calcium hydroxide is titrated by the addition of 40 milliliters of 3.0 molar HCl. Start with the balanced equation. Products, calcium chloride and water. When we balance it, we need a 2 there and a 2 there. So this is a 2-to-1 ratio. I'm going to start once again with liters and molarity. This gives me the moles, which is 0.12 moles of HCl. Then I need to go to moles of calcium hydroxide. So there's 1 mole calcium hydroxide for every 2 moles HCl, which means I'll end up with 0.06 moles of calcium hydroxide. And I know the liters, so 0.06 moles calcium hydroxide divided by 0.0831 liters. You get 0.722 molarity. 3 significant figures because all of the original numbers had 3 significant figures. So those are titration problems. If you have any questions, please bring those questions with you to class tomorrow. We will go over those questions in class.